Hello and welcome to our second video in chapter 1. This one is going to cover sections 1.4 and 1.5. So we're starting in section 1.4 and we're starting with a distinction between physical property and chemical property. Now, property in general is a description about something. And so in chemistry, we really like to break things into categories. And so we break this down into these two categories. And our official definition is that a physical property is something that we can measure or see, observe, without changing what it is. So the examples are smell, taste, color, odor. These are all things that we can figure out without changing what the compound is. Melting point, boiling point, we can melt something or boil it. It doesn't change what it is because we can freeze it or condense it and get back that substance in its original state. All we're doing is a state change. We're not changing the chemical composition. The chemical properties then, in order to observe these, we have to change its substance. We're changing it on that microscopic or that atomic level. So the examples down here are flammability, corrosiveness, acidity, toxicity. These are all things that in order to measure them or observe them, we actually have to react the compound. To know if it's corrosive, we have to let it react with metal to let it see if it will dissolve the metal. In order to know if it's flammable, we have to set it on fire and see how easily it burns. Doing these things, though, changes what the compound is, and so it changes the chemical composition, and we no longer have that original substance. So here's our practice problem, number 44. Classify each of the listed properties of ozone as physical or chemical. So the first one is a bluish color. So color is definitely a physical property. We can see the color, we can observe the color without changing what ozone is. Ozone has a pungent odor. Again, this is physical. We can smell it, and that's something that we can observe without changing what ozone is. Very reactive. Now, the only way we're going to know if ozone is reactive or not is to try to react it. We would have to react it with acids or bases or metals, whatever it is, to see what it's going to do. And when we do that, it changes its structure, so it becomes a chemical property. The next one says that ozone decomposes on exposure to ultraviolet light. Decomposition is a type of chemical reaction. So this is telling us that when ozone reacts with ultraviolet light, it's breaking down into smaller things. It's turning into something else. So this is also a chemical property. And then the last one says that ozone is a gas at room temperature. Well, again, this is something that we can observe without changing what it is. We can look at it just like we could look at a glass of water and know it's liquid. We would know that it's a gas without changing anything. So this is also a physical property. Now, along with physical and chemical properties, we also have to define physical and chemical changes. So we're looking at physical changes first. Now, there are similarities between the definitions of properties and changes. So for example, a physical change does not change the identity of the substance. It doesn't change what it's made of. It just changes what it looks like. So for the examples over here, we have a popsicle melting. So any type of state change, liquid to gas, gas to solid, solid to gas, is considered a physical change because we're changing its state, but we're not changing what it is. We could catch all this liquid popsicle and refreeze it, and we would get our frozen popsicle back. A broken glass, again, it's still glass. It's not changing the fact that it's made of glass. It's just taking another physical state. Dissolving something. So this one might seem a little tricky, but when we dissolve sugar in tea, for example, we could boil away all of that water and get the solid sugar back. So it's just a state change. It's going from a solid to what we call aqueous, and that's a state we'll talk about a lot, just haven't really dealt with it too much yet. And then the last one here is liquid water turning into gas water. So I like this picture because it shows us in the molecule form too. So notice we have a little water molecule here, and we still have little water molecules here. The difference is liquid versus gas, but it's still H2O, it's still water. So physical changes are only changing the physical properties. It's changing what it looks like. Chemical changes, on the other hand, change the chemical structure of whatever it is we're talking about. So it's going through an actual chemical reaction. So our examples, iron rusting. A nail is made out of iron. Here's our little iron atoms. When iron rusts, it's reacting with oxygen in the air to make iron oxide. So now our irons are bonded to oxygens. It's not the same compound anymore. It's gone through a chemical change to make a new chemical. Fireworks exploding. Fireworks are made up of little metal flakes, and they catch on fire to become metal oxides. When leaves change color in the fall, the chlorophyll that makes the leaves green is actually breaking down to make new compounds. So it's losing that green component, and it changes into the reds and the oranges and the yellows that we see. As a banana ages, the changes that it goes through are also a chemical change. As it goes from an unripe green banana to a ripe yellow and then a mushy brown banana, it's going through two things. One is oxidizing. So if you bump it and it gets a little cut or a bruise, it's going through an oxidation. But also our bananas are full of complex sugars. And as it sits longer, the complex sugars break down and become simple sugars. This is also why a banana gets sweeter as it gets older. So all of these are changing what the actual chemical compounds are that are in these substances. Now, one of the things that can make this tricky is that when a physical change occurs, it's only changing the physical properties. But when a chemical change occurs, it's changing the chemical properties, but it's also changing the physical properties, because it's changing what it is. This is a new structure. Iron is silver and hard. Iron oxide is red and flaky. So because the chemical compound changed, its physical properties changed as well. So we look for key words, things like rusting or decomposing or oxidizing. We look for those key words to tell us that a chemical change has occurred. So here's our practice. This is number 44. Classify each change as physical or chemical. So the first one is sugar burns when heated in a skillet. Now I did say that these are tricky, can be tricky to figure out. So one of the ways to think about it is to think about if we can get that original substance back. If we can get the original substance back, then it was just a physical change. If you can't get it back, then that tells you that it was a chemical change. So if sugar burns in a skillet, we can't get the original sugar back. It's going to be good turned into a caramel, but that white sugar is now gone. So this is a chemical change. Sugar dissolved in water. Now, if we want to get that sugar back, we could just boil away the water. So this is a physical change. A platinum ring becomes dull because of abrasion. If you own jewelry and you have a little polishing cloth, you know that all you have to do is clean your jewelry, especially platinum and silver, and it will become shiny again. And so this is a physical change. It's because metals are malleable, so you can change their shape and change what they look like, but not change what it is. Now the last one, a silver service becomes tarnished. Now here's the difference. Abrasion means that something's bumped up against it, scratched it. Tarnished means that it turns black. Silver can react with the oxygen in the air to tarnish. This is silver's version of rusting. So this is a chemical change because we've created silver oxide. one more. So this is number 144. So here's an example of the different editions. So in edition 4 of the book, it's number 144. In edition 3 of the book, it's 142. So just in case you're using an older edition. The diagram shown first represents a solid carbon dioxide, also known as dry ice. Which of the other diagrams best represents the dry ice after it has sublimed into a gas? So here is solid carbon dioxide. Carbon dioxide is CO2, so one carbon with two oxygens. And we can see that. So if we pick out this little molecule right here, there's the black carbon in the center, and there's an oxygen on each side, so CO2. And we know it's a solid first because it tells us it's a solid. But we also know it's a solid because it's really compacted together. Solids are really compact, liquids are not quite as compact, and then gases are much farther apart. So we know that these all represent gases because they're all farther apart. So we have to look at what's different about them. Here, the red molecules and the black atoms are separate from one another. Now I knew that these were molecules and these were atoms because here we have two things together and here we have one separate. So if it's one thing by itself, it's an atom, and if there's two or more, it's a molecule. So this tells us that the carbon is separate from the oxygens. Over here, we have some carbons with oxygens and we have some oxygens together, but there's no consistency. And then over here, I have the carbon in the middle and the oxygen on each side, and they all look the same. So I know that my carbon dioxide gas is letter C. And I know this because they look the same. When a solid sublimes, this is a state change. It's going from a solid into a gas, so it's changing chemically. So I know that these little molecules here are going to be the same as the molecules in my answer. A and B don't represent the same thing. If our CO2 were to turn into A or into B, that would represent a chemical change. And nothing in our problem here mentioned anything about a chemical change occurring. So subliming, melting, boiling, evaporating, these are all state changes, which means they're all physical changes. So our molecules look the same on the atomic level or on molecular level, and all that's occurred is a physical change. All right, last topic in this video is section 1.5, and it's about energy. So this is a very brief introduction to energy. We're going to talk about it in quite a few more chapters. But we talk about energy because in order to do chemical and physical changes, we have to use energy. So our official definition of energy is that it's the capacity to do work. So this definition and the definition of work are something that you'll encounter a lot more in physics. We don't do a whole lot with that exact definition. We use more of general terms. Energy in general that we're looking at is the kinetic and the potential together. So we have a couple definitions down here. Kinetic energy is associated with motion. So there's always an example in a book of a baseball player or a golfer, and as they're swinging, that's kinetic energy. So swinging the bat, kinetic energy. Potential energy is associated with position. So as the bat's resting on a person's shoulder, that is energy that is waiting to be used. Or the water that's right at the top of this waterfall has gravitational energy. It's ready to fall over the cliff. It just hasn't quite done it yet. Another big one for us, potential energy, is why we eat food. Food has energy stored in it, and as we eat it, we can turn it into kinetic energy. Thermal energy is something we will deal with later on in this chapter, and then a lot in Chem 1B. It has to do with temperature and the exchange of heat energy. And then we've talked about the law of conservation of mass. There's also the law of conservation of energy, which says that energy cannot be created or destroyed. So we can definitely transform it. We can turn potential energy into kinetic energy, but we can't gain or lose energy. And so that's also a concept that we'll use in some of the math that we do later on. All right, that's it for this video. Thank you.